Good morning, everyone. Welcome to today's presentation. I'm excited to guide you through the fascinating world of objects and classes in Java. Today's session is titled Unit 2 Objects and Classes, and we'll be exploring the fundamental concepts that form the backbone of Java programming. We'll cover basics like what objects and classes are, how constructors and finalizers work, and delve into visibility modifiers, methods, and objects. Additionally, we'll look at some inbuilt classes such as string, character, string buffer, and file, along with the use of the this reference. So, let's get started and unlock the core ideas behind object-oriented programming in Java. Let's talk about the basics of objects and classes. First, a class is essentially the building block of object-oriented programming. Think of it as a blueprint or a template that defines a particular type of object. It is a user-defined data type, which means we create it ourselves, and it contains both data and functions. These are the behaviors and properties that the objects created from the class will have. Now, an object is an instance of a class. In other words, once we've defined a class, we can create variables of that class type, and these variables are what we call objects. They are specific, concrete realizations of the class, with actual data stored inside them. This connection between classes and objects is fundamental because classes define the structure, and objects are the actual entities that we manipulate in our programs. Understanding this relationship helps us see how object-oriented programming is all about modeling real-world entities efficiently. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Each object has its own variables and functions. What this means is that in programming, every individual object is responsible for managing its own data and behaviors. Instead of sharing everything globally, each object maintains its own set of variables, which store its state, and functions, which define what it can do. This approach helps us create more modular, organized, and reusable code. It also makes debugging easier because you can focus on a specific object without worrying about the entire system. Connecting this to our overall theme, understanding how objects encapsulate their own data and actions is fundamental to building efficient and maintainable programs. Let's take a closer look at the characteristics of an object. First, the state refers to the data or value that an object holds at any given moment. Think of it as the current information stored within the object. Next, behavior describes what an object can do, its functionality. For example, a bank account object might have behaviors like deposit or withdraw. These are the actions that define how the object interacts with other parts of the system. Finally, there's identity. This is a bit more abstract but equally important. An object's identity is usually implemented through a unique ID. This ID isn't visible to users, but internally, the Java virtual machine uses it to distinguish one object from another. This ensures that even if two objects have the same state, they are still recognized as separate entities. Connecting all these points back to our overall theme, understanding these characteristics helps us see how objects are uniquely defined, how they behave, and how their data is managed, crucial concepts in object-oriented programming. All right, let's talk about classes. Remember, a class is a logical entity, so it's not something you can hold in your hand or see physically. Instead, it serves as a blueprint or template for creating objects. When we look at what a class in Java can contain, there are several key components. First, we have fields, which are essentially variables that hold the state or data of an object. Then, there are methods, which define the behaviors or actions that objects of the class can perform. Constructors are special methods used to initialize new objects. Blocks are used for grouping statements, often within methods or constructors. And finally, classes can contain nested classes and interfaces, which are defined within other classes to organize code better or implement specific functionalities. Throughout this presentation, it's important to see how these components work together to define the structure and behavior of objects in Java. Let's take a look at this example of object and class in Java, focusing on the main method within the student class. Here, we define a class called student, which has two fields, an integer id and a string name. These fields represent the data members or instance variables of the class. Inside the student class, we also have the main method, which is the entry point of the program. Now, notice that the main method is placed directly inside the student class. This is important because it shows how we can create objects of the class within its own main method. Inside main, we create a new student object, which we assign to a reference variable called S1. This object is an instance of the student class, and through this reference, we can access the object's data. For example, when we write system out println S1 ID, we're trying to print the value of the id field of that specific object. Similarly, system out println S1 name accesses the name of the same object. This demonstrates how objects and references work together to store and retrieve data. The key takeaway here is that the main method can be inside the class it's working with, and through object creation, we can manipulate and access the data members. This ties into the overall theme of understanding how classes and objects interact in Java to build flexible, modular programs. Now let's take a closer look at this example. Here, we have a simple class called student, which has two attributes, id and name. Notice that we haven't assigned any values to these attributes yet, which is important to keep in mind. Next, we create another class called teststudent1, which contains the main method. This main method is where the program starts executing. Inside it, we create a new student object, named S1, using the new keyword. Then we print out S1 id and S1 name. Since we haven't initialized these variables, they will display default values, 0 for the integer id and null for the string name. This example highlights an important concept. The object creation is happening outside the class, specifically in the main method. It's a good demonstration of how objects are instantiated and how their attributes can be accessed and displayed. Remember, this approach is fundamental to understanding how classes and objects work together, especially when you're writing your own programs. It also connects to the broader theme of object and class examples, illustrating how the main method can be used outside of the class definition to manipulate objects. Now, let's explore the three main ways to initialize an object. First, we have initialization by reference variable. This approach involves creating a reference to an existing object, which can be useful when you want to work with the same object across different parts of your program without copying it. Next, there's initialization by method, where you use a specific method designed to set up or configure the object after its creation. This allows for more flexible and dynamic initialization, especially when the exact setup depends on runtime conditions. Lastly, we have initialization by constructor, which is the most common and fundamental way. Here, the constructor is a special method that gets called automatically when you create a new object, ensuring that the object is properly initialized right from the start. All these methods are important because they give us different options for setting up objects depending on our specific needs, and understanding these methods helps us write clearer, more efficient code within our overall programming approach. All right, let's look at how we initialize objects through references. In this example, we have a class called student, which has two members, id and name. Then, in the teststudent2 class, we create a new student object using the statement student s1 equals new student. Here, s1 is a reference variable that points to this newly created student object. When we write s1 id equals 101 and s1 name equals Sanu, we're assigning values to the members of that object through the reference s1. This is a key concept because it shows how references work in Java. They're like pointers that let us access and modify the actual objects in memory. Finally, the system out println statement outputs the id and name, separated by a space, which illustrates how we can access the object's members through its reference. This process is fundamental because understanding how references and objects interact is crucial for grasping Java's object-oriented nature and managing memory effectively. Let's take a closer look at how initialization is done through methods in Java. Here, we have a class called student, which contains two data members, role, no, and name. The key method here is insertRecord, which takes an integer and a string as parameters. When we call this method, it assigns those values to the respective data members. This allows us to initialize or update the student's information dynamically. Notice how we also have a display information method, which simply prints out the student's roll number and name on the console. Moving on to the main class, Test Student 4, we see that we create two student objects, S1 and S2. Using the insert record method, we assign specific roll numbers and names to each student. Finally, by calling display information on both objects, we can see their details printed out. This example highlights how methods like insert record serve as a convenient way to initialize object data after creation, giving us flexibility and clarity in our code. It also demonstrates the importance of encapsulating data manipulation within methods, which is a core principle in object-oriented programming. Let's take a closer look at this example to understand how classes and objects work in Java. Here, we have a class called employee, which represents an employee with three attributes: id, name, and salary. Notice how we declare these variables as private or default. They store the data specific to each employee. Next, we have the insert method. This method allows us to assign values to the employee's id, name, and salary. You can think of it as a way to initialize or update the employee's information after creating an object. The method takes three parameters: an integer for the id, a string for the name, and a float for the salary. Inside the method, we assign these parameters to the class variables. Then we have the display method. This method outputs the employee's information to the console, combining the id, name, and salary into a single line for easy reading. It's a simple way to see the data stored in each employee object. Moving on to the main method in the test employee class. Here, we create two employee objects, E1 and E2, using the new keyword. This is how we instantiate objects in Java. After creating these objects, we use the insert method to set their respective details. E1 gets assigned with id 101, name Ajit, and salary 45,000, while E2 is assigned with id 102, name Irfan, and salary 25,000. Finally, we call the display method for each employee. This prints their details to the console, confirming that the data has been stored correctly. This example illustrates the fundamental concepts of classes, objects, methods, and how they work together to model real-world entities like employees in a simple and clear way. Now, let's explore the different ways to create an object in Java. This is a fundamental concept because how we instantiate objects impacts how our programs behave and perform. The most common method is using the new keyword, which is straightforward and easy to remember. When we write new, Java allocates memory for the object and calls its constructor, initializing it for use. But there are other interesting ways too. For example, we can use factory methods. These are static methods that return instances of a class. They provide more control over object creation, like choosing between different implementations or adding caching mechanisms. Another technique involves cloning objects, where an existing object is duplicated. This can be useful when creating a copy of an object without going through the constructor again. Lastly, with newer Java features, like reflection, we can create objects dynamically at runtime, which adds a lot of flexibility, especially in frameworks or libraries that need to instantiate classes without knowing their types at compile time. Understanding these different approaches helps us write more flexible, efficient, and maintainable code. It also ties into our overall theme of mastering object-oriented programming by knowing the tools Java offers for object creation. Let's take a closer look at anonymous objects in Java. When we write new calculation, without assigning it to a variable, we're creating what's called an anonymous object. Now, this object exists just for that immediate purpose and can't be referenced later. On the other hand, if we do calculation C equals new calculation, we're creating an object and storing it in a variable named C. This allows us to call methods through that reference, like C, fact, 5. This approach is useful when we need to reuse the object or call multiple methods on it. Another interesting point is that we can call a method directly on a new anonymous object, like new calculation, fact, 5. This creates the object, calls the method, and then the object is discarded immediately after. Connecting this to our overall theme, understanding when to use anonymous objects versus named references helps us write cleaner, more efficient code. It allows us to manage object life cycles effectively and choose the right approach based on our specific needs. Now, in this slide, we're exploring how to create multiple objects of the same type, which in this case is the rectangle class. As you can see, we declare two objects, R1 and R2, both of type rectangle. This allows us to handle multiple rectangles independently, each with its own set of properties. The insert method is used to assign specific dimensions to each rectangle, so R1 is set to 11 by 5, and R2 to 3 by 15. Then, by calling the calculate area method on each object, we compute and display their respective areas. This example highlights an important concept. Creating multiple objects from the same class enables us to manage different data sets simultaneously, which is fundamental in object-oriented programming. It also demonstrates how each object maintains its own state and how methods operate on that specific state. Overall, this approach allows us to efficiently handle multiple similar entities without redundant code, tying into our broader theme of reusability and modular design in programming. Now, let's talk about what a method actually is. A method is essentially a block of code or a collection of statements that are grouped together to perform a specific task or operation. Think of it as a mini program within your program, designed to do one particular thing. It only runs when we explicitly call or invoke it, so it's a way to organize and reuse code efficiently. When we declare a method, we're providing some important information about it. This includes attributes like its visibility, whether it's accessible from other parts of the program or not, its return type, which tells us what kind of data it will give back after running, its name, and any arguments or parameters it might need to do its job. Understanding methods is crucial because they help us break down complex tasks into manageable pieces, making our code more organized, readable, and maintainable. Throughout this presentation, keeping this concept in mind will help us see how methods fit into the bigger picture of programming and software development. Now, let's talk about access specifiers, which are essentially the access modifiers that determine how and where methods can be accessed in Java. They play a crucial role in controlling the visibility of methods within your application, helping you enforce encapsulation and security. Java provides four main types of access specifiers. First, we have the public access specifier. When a method is declared as public, it means that it can be accessed from any other class in your entire application. This is useful when you want to make a method widely available. Next is private. If you declare a method as private, it becomes accessible only within the class where it is defined. This is great for hiding internal details and protecting data from outside interference. Then we have protected. A protected method can be accessed within the same package, or in subclasses even if they are in different packages. This provides a middle ground between public and private, offering controlled access for inheritance purposes. Finally, there's the default access, which comes into play when you don't specify any access modifier at all. In that case, Java assigns default access, meaning the method is accessible only within the same package. It's a way to restrict access more tightly without explicitly declaring something as private or protected. Understanding these access specifiers is key to designing robust, secure, and well-structured Java applications. They help you control which parts of your code are exposed and which are kept internal, aligning with the overall goal of writing clean, maintainable code. In this slide, we're looking at a simple Java program that demonstrates two important concepts, using built-in methods and defining our own methods. First, notice the class named Demo, which contains the main method, the entry point of any Java application. Inside the main method, we use systemoutprint to display a message, specifically the maximum of two numbers. We do this by calling mathmax with the arguments 9 and 7. This illustrates how Java provides utility classes like math that include ready-to-use methods for common operations, simplifying our code. Now, beyond that, I want to draw your attention to the user-defined method shown here, findEvenOdd. This method takes an integer input and checks whether it's even or odd by using the modulus operator. If the number divided by 2 leaves no remainder, it's even, otherwise, it's odd. Notice how the method uses a simple if-else statement to determine the result and print an appropriate message. Connecting this to our overall theme, these examples highlight the power of Java's built-in functions combined with the flexibility of creating our own methods. It's all about writing clean, reusable code that makes our programs more efficient and easier to understand. Let's talk about static methods. A static method is a method that belongs to a class rather than to any specific instance of that class. This means you can call it without creating an object first. One of the key things about static methods is that they can access static data members of the class, and they can even modify their values. This is useful when you want to perform some operation that's related to the class itself, rather than any particular object. Static methods are often used to create instance methods, especially when you need a utility function that doesn't depend on object state. To call a static method, you simply use the class name followed by the method name, which makes it clear that you're working at the class level. A very common example of a static method is the main method in many programming languages. It acts as the entry point for the program and doesn't rely on an instance of the class to run. So, understanding static methods is crucial because they play a central role in structuring your code efficiently and clearly. Now, let's take a closer look at the instance method in this example. First, notice that we have a class called instance_method_example. Inside the main method, we create an object of this class, which is essential because instance methods are called on objects, not directly from the class. So, we write instance_method_example obj equals new instance_method_example to instantiate our object. Next, to invoke the instance method, which in this case is add, we use the object we just created, obj add1213. This is a key point. Since add is not static, we need an object to call it. When we do that, it calculates the sum of the two numbers, 12 and 13, and then prints out the result with system, out, println. Now, focusing on the method itself, it's defined as public int add, int a, int b. Since we haven't used the static keyword, this is what we call a user-defined method, meaning it's specific to instances of the class. Inside the method, we add the two parameters, a and b, and store the result in a variable called s. Finally, we return s, which gives us the sum back to the caller. This example helps illustrate how instance methods work by requiring an object to be called and enabling us to perform specific operations associated with that object's data. This is a fundamental concept as we build more complex programs that rely on object-oriented principles. Now, let's look at the two main types of instance methods in Java: accessor methods and mutator methods. These are fundamental for managing how data is accessed and modified within objects. An accessor method, like getId, is used to retrieve or access the value of a private variable. In this example, calling getId will return the current value of id. It's a way to safely expose data without giving direct access to the variable itself. On the other hand, mutator methods, such as setRole, intRole, are used to modify or update the value of a variable. In this case, setRole takes a parameter called role and assigns it to the object's role variable using thisRole equals role. This encapsulation ensures controlled modification of data, maintaining the integrity of the object. These methods are key to the concept of encapsulation, which is a core principle in object-oriented programming. They allow us to hide the internal state of an object while still providing controlled access. So, understanding and properly implementing accessor and mutator methods helps us create more robust, maintainable, and secure code. They are essential tools for managing object data effectively within our overall programming design. All right, let's talk about the abstract method. So, an abstract method is a method that doesn't have a body or implementation. Essentially, It's just a declaration, not a full method. You always declare these in an abstract class. Now, if a class contains at least one abstract method, that class itself must be declared as abstract. To create an abstract method, you simply use the keyword abstract. This concept is important because it defines a contract for subclasses, ensuring they implement specific behaviors while allowing the parent class to remain incomplete on its own. It ties into our overall theme of designing flexible, extensible code structures. All right, let's take a closer look at the slide. Here, we see an example of an abstract class in Java, named Demo. An abstract class is a class that cannot be instantiated on its own, which means you can't create objects directly from it. Instead, it's meant to be extended by subclasses. In this case, we have an abstract method called display, which is declared but not implemented in Demo. This indicates that any subclass inheriting Demo must provide its own implementation of the display method. Moving on to the MyClass class, it extends Demo, which means it inherits from the abstract class. Inside MyClass, we see the implementation of the display method. Here, it simply prints out abstract method, a simple way to demonstrate how the subclass provides concrete behavior for the abstract method. Now, in the main method, there's a commented line that shows creating an object of the abstract class Demo, but it's commented out because, as we know, we can't instantiate an abstract class directly. Instead, you would create an object of MyClass, which is a concrete subclass that implements the abstract method. This example highlights a key concept. Abstract classes serve as a blueprint for other classes, enforcing certain methods to be implemented while allowing flexibility in how they're defined. It ties into our overall theme of understanding object-oriented programming principles, specifically, how abstraction helps us design flexible and reusable code structures. Let's talk about constructors. A constructor is a special block of code that looks similar to a method, but its main job is to initialize objects. When you create an instance of a class, the constructor is called automatically. At that moment, the memory for that object is allocated, meaning the system sets aside space to store all the object's data. What makes constructors unique is that they are specifically used for initialization. Every time you use the new keyword to create an object, at least one constructor gets invoked. If you haven't defined any constructors in your class, the system automatically calls a default constructor, which is provided implicitly. This concept ties into our overall theme of understanding how objects are created and set up in programming. Constructors ensure that every object starts in a consistent and usable state, making them a fundamental part of object-oriented programming. Let's talk about the rules for defining constructors in Java. First, the constructor name must exactly match the name of its class. This is important because it helps Java identify it as a constructor, not a regular method. Second, a constructor must not have an explicit return type. Unlike other methods, constructors don't specify a return type at all. Additionally, there are some restrictions on what Java constructors can be. They cannot be abstract, static, final, or synchronized. These rules help maintain the purpose of constructors, which is to initialize new objects. Now, there are two main types of constructors. The first is the default constructor, which is a no-argument constructor that Java provides automatically if you don't define any. The second is the parameterized constructor, where you can pass specific values at the time of object creation to customize the initialization process. Understanding these rules and types is fundamental as we delve deeper into object-oriented programming, ensuring our constructors are correctly defined and used to create flexible, well-structured classes. Let's take a closer look at the difference between a default constructor and a parameterized constructor. On this slide, we see an example of a default constructor inside the Bike1 class. It doesn't take any arguments, and when we create a new object of Bike1, it simply prints out bike is created. This helps us understand that default constructors initialize objects with default values or just perform basic setup. Now, notice in the main method, we create a new Bike1 object with the line Bike1b equals new Bike1. When this line executes, the default constructor runs automatically, and the message is displayed. This is a simple way to see how constructors work without needing to pass any parameters. Moving on to the Student4 class example, here we see objects being created with specific values, like Student4 S1 equals new Student4, 111, Karen, and Student4 S2 equals new Student4, 222, Arian. These are examples of parameterized constructors because they accept arguments to initialize the objects with specific data right at creation. After creating these objects, we call their display methods to show their values. This demonstrates how parameterized constructors allow us to set up objects with customized data immediately, making our classes more flexible and useful. Connecting this to our overall theme of object-oriented programming, understanding when and how to use default versus parameterized constructors is essential. It helps us control object initialization effectively, whether we want simple default setups or customized data at creation time. Now let's look at constructor overloading in Java. In this example, we have a class called Student5. Inside this class, we have 3 fields, id, name, and age. Notice that we've created 2 constructors with different parameters. The first constructor takes 2 arguments, I and n, which represent the student's ID and name. Inside this constructor, we assign these values to the respective fields. The second constructor takes 3 arguments, I, n, and a which stand for ID, name, and age. Here, we assign the age as well as the ID and name. This is the core idea of constructor overloading, having multiple constructors with different parameter lists, allowing us to create objects in different ways depending on what information we have. In the main method, we create 2 instances of Student5. The first, S1, uses the 2-argument constructor, so only the ID and name are set. The second, S2, uses the 3-argument constructor, setting all 3 fields. When we call the display method on both objects, they show their respective data. Now, I want to highlight an important point. In Java, constructors are special methods used to initialize objects. Constructor overloading is a way to provide flexibility in object creation. Finally, the slide mentions the difference between constructors and methods in Java. Remember, constructors are used specifically for initializing new objects and don't have a return type, whereas methods perform actions and can return values. This distinction is fundamental to understanding how Java handles object creation and functionality. Now let's take a look at the Java copy constructor. In this example, we have a class called Student6. It has 2 member variables, id and name. The first constructor initializes these variables with specific values, like an ID and a name. The second constructor is the copy constructor, and it's used to create a new object by copying an existing one. Here, it takes another Student6 object as a parameter and copies its id and name into the new object. This is particularly useful when you want to duplicate objects without sharing references. In the main method, we create a student S1 with ID 111 and name Karen. Then, we create S2 by passing S1 to the copy constructor. When we call the display method on both S1 and S2, you'll see that they have the same values, but they are distinct objects in memory. Using copy constructors helps us manage object duplication cleanly and safely, which is an important concept in object-oriented programming. It ensures that each object maintains its own separate state, even if they start out with the same data. Let's look at this example where we're copying values without using a constructor. Here, in the main method, we create a Student7 object S1 with an ID of 111 and name, Karen. Then, we create another Student7 object S2 using the default constructor, which doesn't set any initial values. Notice that instead of copying the entire object, we're manually assigning S1's id and name to S2. This is a key point, because it shows how copying values directly can be error-prone and cumbersome. Now, why do we need a constructor in the first place? Well, the constructor's main purpose is to initialize objects with specific values right when they are created. It makes our code cleaner, more efficient, and less prone to mistakes. Instead of manually assigning each attribute after object creation, a constructor does that setup automatically. This example ties back to our overall theme of object-oriented programming, making code more organized, readable, and maintainable. Using constructors simplifies object creation and ensures objects are always initialized properly from the start. Let's talk about the static keyword and static variables. A static variable is used when you want to refer to a property that is common to all objects of a class. For example, think about the company name for all employees or the college name for all students. These are properties that don't change from one object to another, so it makes sense to define them as static. One important point to remember is that static variables get allocated memory only once, and that happens in the class area when the class is loaded. So, no matter how many objects you create, there's only one copy of the static variable. Let's look at this example with a student class. Here, we have an instance variable for roll number and name, but the college name is a static variable. Notice that the static variable college is initialized directly within the class, outside of any method or constructor. In the constructor, we set the individual roll number and name for each student, but the college name remains the same for all students because it's static. And in the display method, when we print out the details, the college name will be the same for every student object, thanks to the static variable. This concept helps us efficiently manage data that's shared across multiple objects without duplicating memory. This slide doesn't contain enough information. That's why we're moving to the next slide. So let's talk about static methods. A static method belongs to the class itself rather than to any individual object of that class. This means you don't need to create an instance of the class to use it. You can call a static method directly through the class name, which makes it quite convenient in many cases. Another key point is that static methods can access static data members. They can also modify the value of these static variables. This is important because static data members are shared across all instances, so static methods can be used to manipulate shared data efficiently. In the context of our overall discussion on class design, static methods are useful for utility functions or operations that don't depend on the state of a particular object. They help organize code logically within the class structure, making your programs cleaner and more manageable. Let's take a closer look at this example. Here, we have a class called Calculate. Inside this class, there's a static method named cube, which takes an integer as input and returns its cube, or multiplied by itself 3 times. This static method is a key concept because it allows us to call it directly on the class itself without needing to create an instance. In the main method, we see how this method is used in practice. We call calculateCube with the argument 5, which calculates 5 cubed, and store the result in a variable called result. Then, we print out this result, which will display 125. The important idea here is how static methods work. They belong to the class rather than any particular object, making them useful for utility functions like this one. This example ties into our overall theme of understanding how to organize and reuse code efficiently in Java, demonstrating how static methods can simplify our programming tasks. All right, let's take a closer look at this slide. Here we see the static block, which is used to initialize static data members in a class. Think of it as a setup step that prepares the class before anything else happens. Now, an important point to remember is that this static block runs automatically before the main method, and it does so at the time of class loading. In the example with class A2, notice how the static block contains a print statement. When we run this program, you'll see that message printed first, even before hello main. This illustrates how the static block executes first, setting the stage for the rest of the program. So the key takeaway here is that static blocks are a powerful tool for initializing static data, and they execute exactly once, right when the class is loaded into memory, prior to main. This behavior is crucial to understand because it influences the order of execution and initialization in your programs. Connecting this to our overall theme, static blocks help us control the startup process of our classes. ensuring that any necessary setup is completed before the program proceeds further. Let's take a closer look at this reference. What I want to highlight here is how important it is to rely on credible and well-documented sources when we're building our understanding or making decisions. This particular reference serves as a foundation for the data or concepts we've discussed so far. When we cite reliable sources, it not only strengthens our arguments, but also helps us maintain transparency and trustworthiness. Remember, in the broader context of this presentation, the goal is to ensure that our insights are grounded in solid evidence. So, always pay attention to where your information is coming from and make sure it's reputable. This approach ultimately supports the overall theme of accuracy and credibility that runs throughout our discussion. Now, let's talk about this keyword, which is used to refer to the current class instance variable. Understanding this concept is important because, without using this keyword, there can be some confusion or errors in assigning values. In the example here, we have a student class with variables like role, name, and fee. Inside the constructor, we try to assign the parameters to the instance variables. But notice, since the parameter names are the same as the instance variables, using just role equals role actually just assigns the parameter to itself, not to the class variable. That's where this keyword comes into play. If we write this, role equals role, it clearly indicates that we're assigning the parameter role to the instance variable role. Without this keyword, the program might not behave as expected because the local parameters hide the instance variables. So, using this helps us explicitly refer to the current object's variables, making the code clearer and avoiding bugs. In the overall context of object-oriented programming, this keyword is vital for clarity, especially when dealing with constructors or methods where local variables shadow class variables. Now let's take a closer look at the solution to our problem, which revolves around defining and using a class named student. Here, we start by declaring the class with the keyword class followed by the class name student. Inside the class, we define 3 data members, an integer roll number, a string name, and a float fee. These variables represent the essential attributes of a student. Next, we have the constructor method, which is a special method used to initialize objects. The constructor takes 3 parameters, role, name, and fee. Inside the constructor, we assign these parameter values to the class's data members using the this keyword. This helps differentiate between the class variables and the parameters with the same names. Following that, we have a display method, which is a simple function to output the student's details. It uses system, out, println to print the roll number, name, and fee, all separated by spaces. This makes it easy to see each student's information clearly. Moving on to the main class, test this, where the main method serves as the entry point of the program. In here, we create 2 student objects, S1 and S2. For S1, we pass 111 as the roll number, Ankit as the name, and 5000F as the fee. For S2, we pass 112, Sumit, and 6000F respectively. When we call the display method on each object, it prints out their details. This example demonstrates how to instantiate objects, initialize their data members through constructors, and invoke methods to display their data. It's a fundamental concept in object-oriented programming, showing how classes and objects work together to model real-world entities effectively. Now let's look at this point. This, to invoke current class method. Here, we're talking about using the keyword this in programming, which is essential when we want to call or refer to a method within the same class. Think of this as a way to tell the program, hey, I'm talking about the current object or instance we're working with. It helps us distinguish between local variables and class members, especially when they have the same name. So when you see this used to invoke a method, it's a clear signal that we're calling a method belonging to the current class instance. This is particularly important in object-oriented programming because it maintains clarity and ensures we're interacting with the right object context. Remember, understanding how to invoke class methods correctly is fundamental as we build more complex and modular code, keeping our programs organized and predictable. Now let's look at the third point, this, which is used to invoke the current class constructor. In this example, we're calling the default constructor from within a parameterized constructor. When we create an object of class A with a parameter, the constructor that takes an integer is executed. Inside that constructor, the call to this invokes the default constructor of the same class, which prints hello. After that, the value of x is printed. This demonstrates how this helps us reuse constructor code within the same class, promoting cleaner and more efficient code. Remember, this must be the very first statement in the constructor. Connecting this to our overall theme, understanding constructor chaining with this, is essential for designing flexible and maintainable classes in Java. Now let's take a closer look at this example. We have a class called A which has two constructors. The first one is the default constructor, A, and inside it, we see a call to this, 5. This means that when we create an object using the default constructor, it actually calls the parameterized constructor with the value 5. After that, it prints hello. The second constructor, A, int, simply prints the value of x. So, when we create an instance of class A using the default constructor, it first calls the parameterized constructor with 5, which prints 5, and then it proceeds to print hello. This example is a great illustration of how a default constructor can invoke a parameterized constructor using the this keyword. It emphasizes the importance of constructor chaining, which helps in code reuse and maintaining consistency. In the main method of class test.this, we create a new object of class A using the default constructor. As a result, you'll see the output of 5 followed by hello. This demonstrates how constructor chaining works in practice, and it's a useful technique when designing classes that require multiple constructors. Overall, this example highlights how you can call a parameterized constructor from a default constructor, and why that can be beneficial for cleaner, more organized code. So in this slide, we're looking at how to pass an object as an argument in a method. Here, we have a class S2 with a method named m that takes an object of type S2 as a parameter. This is a common technique in Java to enable objects to interact with each other or perform operations based on other objects. Notice that inside the method p, we're calling m, this. The keyword this refers to the current instance of the class. So by passing this to the method m, we're essentially passing the current object itself as an argument. This pattern is very useful because it allows a method to work with or manipulate the object that called it. It's like giving the method a reference to the current object so it can operate on it or pass it around as needed. Finally, in the main method, we create an instance of S2 called S1, and then we call S1p. When we do this, the p method executes, which in turn calls m, this, passing the current object S1 to the method m. This example really highlights how the concept of passing this as an argument can be used to facilitate object interactions within a class. It's a fundamental idea that underpins many design patterns and object-oriented programming techniques. Now let's look at how we pass an object as an argument in the constructor call. In this example, class B has a constructor that takes an object of type A4. When we create an instance of class B inside the A4 constructor, we pass this as the argument. Remember, this refers to the current object of the class. So essentially, we're passing the current A4 object to be inside B. We store this object in a member variable called obj. Later, in the display method, we access the data member of the A4 object that was passed in. This demonstrates how object references can be used to establish a connection between objects, allowing them to interact. This pattern is fundamental in object-oriented programming because it enables objects to communicate and collaborate effectively. So, in summary, passing this as an argument allows one object to give a reference of itself to another, facilitating tighter integration and data sharing between objects. All right, let's take a closer look at this slide. Here, we're exploring the keyword this, which is used to return the current class instance. In our example, we have a class A with a method getA that returns this. Essentially, this refers to the current object of the class. Now notice how in the main method, we create a new object of class A and immediately call getA, which returns that same object. Then, we chain the call to the MSG method, which prints Hello Java. The key point here is that using this allows us to return the current object, which can be very useful for method chaining or fluent interfaces. It emphasizes how this helps us work with the current instance, especially when we want to pass the object around or invoke methods on it seamlessly. Connecting this to the broader theme, understanding this is fundamental for writing more flexible and readable object-oriented code. It streamlines method calls and object references, making your code more intuitive and manageable. Let's talk about the keyword final. When we use final with variables, it means that once a value is assigned to that variable, it cannot be changed later. Think of it as locking in that value. It's set in stone. If we try to modify it after initialization, the compiler will throw a compile time error. This is a useful feature because it helps us prevent accidental changes to important values that should remain constant throughout the program. So, in summary, final ensures immutability for variables after their initial assignment, adding an extra layer of safety and clarity to our code. All right, so on this slide, we're focusing on the concept of declaring a method as final. When we use the keyword final with a method, it essentially means that this method cannot be overridden in any subclass. This is a crucial point because it helps in maintaining the integrity of the method's implementation. By declaring a method as final, we are signaling that its behavior should remain consistent and unaltered, which can be especially important for security or stability reasons. This ties back to our overall theme of understanding how to control and safeguard the behavior of our classes and methods in object-oriented programming. So remember, final methods are a way to prevent modifications and ensure consistency across subclasses. Let's talk about the keyword final when used with classes. When we declare a class as final, it essentially means that this class cannot be extended or subclassed by any other class. So, no other class can inherit from a final class. This is useful when we want to prevent modification or extension of certain classes for security or design reasons. It helps ensure that the behavior of that class remains consistent and unaltered. Connecting this to our overall theme, understanding when and why to use final classes is crucial for designing robust and secure applications. All right, let's take a closer look at this example to understand how the final keyword works in Java. Here, we've defined a class called G and marked it as final. This means that no other class can inherit from class G, which is an important aspect of final classes. Inside the class, there's a method H, which by default is not final, so it can be overridden if needed, unless the class itself is final. We also see a static variable J, initialized to 30. Since it's static, it belongs to the class rather than any instance, and we can modify it directly. In the main method, we change the value of J to 36 and then print it out. This part illustrates that static variables can be modified within the class. Overall, this slide emphasizes the use of the final keyword with classes and the default behavior of methods and variables. Remember, marking a class as final prevents inheritance, and if you want to make sure a method cannot be overridden, you declare it as final as well. This ties into the broader theme of controlling inheritance and method behavior for better code safety and design. Now let's take a closer look at inbuilt classes, starting with the Java string class. Here, we see an example where we initialize a character array, ch, with individual characters like J, a V, a followed by other characters to form the word Java program. Using this character array, we can create a string object simply by writing string s equals new string, ch. This approach is equivalent to directly assigning a string literal, like string s equals Java program. The key takeaway here is that Java provides built-in classes like string that make handling text much easier. Whether you're creating a string from individual characters or directly assigning a string literal, the string class handles all the complexities behind the scenes. This flexibility is part of what makes Java a powerful language for working with text data. So, understanding how these inbuilt classes work helps us write cleaner and more efficient code, especially when dealing with strings and text manipulation. It ties back to our overall theme of leveraging Java's built-in capabilities to simplify programming tasks. All right, let's dive into the two main ways to create string objects in Java. First, we have creating strings by using string literals. For example, when I write string s equals welcome, I'm directly assigning a string literal to the reference variable s now. If I create another string with string s1, welcome, and then s2 equals welcome, notice that both s1 and s2 point to the same string instance in the string pool. This is important because it doesn't create new objects for identical literals, which helps with memory efficiency. Next, we have creating strings with the new keyword. For instance, if I write string s equals new string, welcome, this explicitly creates a new string object in the heap, regardless of whether an identical string exists in the pool. This operation results in two objects, one in the string pool and one in the heap, plus the reference variable points to the heap object. Understanding these two methods is crucial because they impact memory management and performance, which ties back to the broader theme of writing efficient Java code. Recognizing when to use string literals versus the new keyword helps us optimize our applications effectively. All right, let's take a closer look at this example to understand how strings are created in Java. First, we have a class called stringExample, which contains our main method. Inside the main method, the first line shows creating a string using a Java string literal, which is simply assigning a sequence of characters enclosed in double quotes to a variable s1. This is the most common way to create strings in Java because it's straightforward and easy to read. Next, we see an array of characters being defined, called ch, with individual characters like s, t, r, and so on. Then, we create a string s2 by passing this character array to the string constructor. This demonstrates converting a character array into a string, which can be useful when you manipulate characters directly before forming a string. Then, we have another string s3, which is created using the new keyword and the string constructor, passing in the literal example. This shows a more explicit way of creating a string object, although it's less common than using string literals directly. Finally, the system. Out. Println statements print out each of these strings, so you can see the actual string content on the console. The key takeaway here is understanding the different ways to create strings in Java, using literals, character arrays, and the new keyword, and how each method can be useful depending on the context. This ties into the overall theme of understanding string manipulation and object creation in Java. Let's take a closer look at some of the key methods available in the Java string class. First, the charat method. It allows us to retrieve the character at a specific index within a string. For example, if we want to access the third character, we specify index 2 since indexing starts at 0. Next, we have the length method. This one is quite straightforward. It tells us how long the string is, which is useful for loops or validations. Moving on, the static format methods are powerful for creating formatted strings. The first version takes a format string along with variable arguments to produce a customized string. The second version adds locale support, which is essential for internationalization, ensuring our strings are formatted correctly for different regions. The substring methods help us extract parts of a string. The first version takes a begin index and returns the substring from that point to the end. The second version allows us to specify both begin and end indices, giving us more control over the exact portion we want. The contains method is handy for checking if a string includes a certain sequence of characters. It returns true if the sequence is found and false otherwise. This is useful for validation or search operations. Then, the join method helps us concatenate multiple strings with a specified delimiter. Imagine joining a list of words with commas or spaces. This method simplifies that process. Finally, the equals method compares two strings for equality. It checks whether the content of the string matches another object, which is fundamental for comparisons in our programs. Overall, these methods provide a rich toolkit for manipulating strings efficiently and effectively, tying back into our broader goal of mastering Java programming. Let's take a closer look at some of the key methods available in the string class. First, isEmpty is a simple but useful method. It checks whether a string is empty, meaning it has no characters at all. This is particularly helpful when you want to verify user input or ensure data integrity. Next, we have concat. Think of this as adding one string to the end of another. It's a way to combine strings dynamically. Moving on, replace has two forms. The first replaces all occurrences of a specific character with another character, which is useful for quick substitutions. The second replace method works with char sequence, so you can replace entire substrings, not just single characters. This flexibility helps when modifying parts of a string based on more complex patterns. Now, the equals ignore case method is a way to compare strings without worrying about case differences. This is great when you're checking for equality, but want to ignore whether letters are uppercase or lowercase. The split methods are powerful for breaking strings into arrays based on a regular expression pattern. One version lets you split without limits, while the other allows you to set a limit on how many parts you want. This is especially handy for parsing data or processing input. Then there's intern, which returns a unique version of a string from the string pool. This can be useful for memory management or when you need to compare strings efficiently. Finally, indexOf helps you find the position of a character within a string. You can specify just the character or also define a starting point for your search, making it flexible for various scenarios. Overall, these methods give you a robust toolkit for manipulating and analyzing strings, which is essential for handling text data effectively in your programs. Let's take a closer look at some of the key string methods we often use in Java. Starting with indexOf, this method helps us find the position of a specific substring within a string. When we call int index of string substring, it returns the index where that substring first appears. If the substring isn't found, it returns. There's also an overloaded version, int index of string substring int from index, which allows us to specify a starting point for the search. This is useful when we need to find subsequent occurrences of a substring within a string. Moving on, the to lowercase method converts all characters in a string to lowercase, making it helpful for case-insensitive comparisons. There's also a variant, to lowercase, locale, which lets us specify a locale, ensuring the conversion respects locale-specific rules. Similarly, the to uppercase method transforms all characters to uppercase, with an overload that accepts a locale parameter for locale-specific behavior. Next, the trim method is quite handy for cleaning up user input or processing text, as it removes any spaces from the beginning and end of the string. Finally, we have valueOf, a static method that converts different data types, like integers, into their string representation. This is especially useful when we need to concatenate numbers with text or display numbers in the UI. Overall, these methods are fundamental for string manipulation, and understanding when and how to use them helps us write more robust and flexible code. Let's take a closer look at the Java lang string class. This class is quite powerful because it not only represents a sequence of characters, but also implements several important interfaces. Specifically, it implements serializable, which allows string objects to be easily saved or transmitted, making them persistent or shareable across different parts of a program. It also implements comparable, meaning strings can be compared to each other, which is essential for sorting and ordering operations. Lastly, it implements char sequence, an interface used to represent a sequence of characters in a flexible way. Now, speaking of char sequence, this interface is quite fundamental because it provides a way to work with any object that can be viewed as a sequence of characters. This includes not just string, but also classes like string buffer and string builder. These classes are all different ways to create and manipulate strings in Java. So, what does this mean for us? Essentially, Java offers multiple classes to create strings, each with its own use case. String is immutable, making it safe for sharing across threads, while string buffer and string builder are mutable, which makes them more efficient for cases where you need to modify the string frequently. Connecting all these points, Understanding the string class and the char sequence interface helps us see how Java provides both flexibility and robustness in handling textual data. It's a key concept that underpins many operations in Java programming, whether you're storing, comparing, or manipulating strings. Let's take a closer look at the Java string buffer class. This class is used to create mutable or modifiable string objects, which means you can change the content after it's created. This is especially useful when dealing with scenarios that require frequent modifications to strings. Now, on this slide, we focus on the important constructors of the string buffer class. These constructors are essential because they determine how we initialize our string buffer objects. Understanding these will help us efficiently create and manage mutable strings in our Java programs. So, as we go through these constructors, keep in mind how each one can be suited to different situations depending on your needs for size, initial content, or capacity. This ties back to our overall goal of writing more flexible and efficient code. Now, let's take a closer look at some of the most important methods of the string buffer class. First up is append. This method is used to add a specified string to the end of the existing string buffer. It's quite versatile because it's overloaded to handle different data types like characters, booleans, integers, floats, and doubles. So, whether you're adding a simple character or a complex number, append has you covered. Next, we have insert. This method allows us to insert a string at a specific position within the existing string. You specify the position with an index, and just like append, insert is overloaded to handle various data types, including characters, booleans, integers, floats, and doubles. It's really useful when you need to insert data somewhere in the middle of your string. Then there's replace. This method is used to replace a section of the string, defined by a start index and an end index, with a new string. It's perfect when you want to modify a specific part of your string without rewriting the whole thing. Following that, we have delete. As the name suggests, delete removes a portion of the string between two specified indices. It's handy for trimming or removing unwanted parts efficiently. Moving on, reverse is a simple yet powerful method that reverses the entire string. This can be particularly useful in scenarios like palindrome checking or simply revering data for specific processing needs. Lastly, there's capacity. This method returns the current capacity of the string buffer, which is basically the amount of storage allocated. Understanding capacity helps in managing memory efficiently, especially when working with large or dynamic strings. These methods collectively give us a robust toolkit for manipulating strings dynamically, which ties back to our overall theme of efficient string handling in Java. Let's take a closer look at some important methods of the string buffer class. First up is ensure capacity. This method helps us make sure that the buffer has at least the minimum capacity we specify. It's useful when we know we're going to be adding a lot of data and want to avoid unnecessary resizing. Next, we have charat. This method allows us to retrieve the character at a specific position within the string. It's very handy when we need to examine individual characters, perhaps for validation or processing. Then there's length. As you might expect, this returns the total number of characters in the string buffer. It's fundamental for understanding how much data we're working with. Moving on, we have substring with one parameter. This method extracts a portion of the string starting from a given index to the end. It's useful when you need a specific segment of your data. Finally, there's the substring method with two parameters, begin index and end index. This allows us to extract a specific portion of the string between two positions, exclusive of the end index. It gives us precise control over the parts of the string we want to work with. All these methods are key to effectively manipulating string buffer objects, which are essential for dynamic string operations in Java. They help us manage memory efficiently and perform targeted string modifications, aligning with our overall goal of writing flexible and efficient code. All right, let's take a closer look at the string buffer class and its append method. In this example, we start by creating a new string buffer object called SB, initialized with the text hello. Then we use the append. method to add Java to this string buffer. It's important to note that the original string inside the string buffer is changed directly. This is what makes string buffer mutable. So after appending, when we print SB, it outputs hello Java. This demonstrates how the append method is a simple and efficient way to build or modify strings dynamically. Understanding this mutable behavior is key when working with string buffer in your Java programs, especially for performance-critical applications. Now let's look at how the insert method works with string buffer. In this example, we start by creating a string buffer object named SB with the initial value hello. Then, we use the insert method to insert the word Java at position 1. This is a key point because unlike string concatenation, insert allows us to add text at a specific position within the existing buffer. After the insertion, the original string is modified, and when we print SB, the output is HJavelo. This demonstrates how string buffer's insert method provides a flexible way to manipulate strings dynamically, which is especially useful when building or modifying strings in a program. This method helps us understand the importance of mutable string objects in Java, aligning with our overall theme of efficient string handling. All right, let's take a closer look at the string buffer replace method. In this example, we've created a class called string buffer example3 with a main method. Inside, we initialize a string buffer object called SB with the word hello. Now, the key part here is the replace method. It takes 4 parameters: the start index, the end index, and the string to replace with. In our case, we're replacing characters from index 1 to 3 with the word Java. Remember, the replace method is inclusive of the start index but exclusive of the end index, so it replaces characters at positions 1 and 2. After the replacement, when we print SB, it outputs HJavelo. Notice how the original E and L from hello are replaced, and Java is inserted in their place. This demonstrates how powerful and flexible the replace method can be for modifying parts of a string buffer. And as you'll see throughout this presentation, understanding these string manipulation methods is essential for efficient coding in Java. Now let's take a closer look at the delete method of the string buffer class. In this example, we create a string buffer object with the initial value hello. Then we call the delete method, specifying the start index as 1 and the end index as 3. Remember, the delete method removes characters from the specified start index up to, but not including, the end index. So in this case, it removes the characters at positions 1 and 2, which are E and L. After this operation, when we print the string buffer, the output is HLO. This demonstrates how the delete method can be used to efficiently remove specific parts of a string, which is a common task when manipulating text data. It's a powerful tool in the string buffer class that helps us modify strings dynamically without creating new objects. All right, let's talk about the reverse method of the string buffer class. In this example, we create a string buffer object named SB initialized with the word hello. When we call SB reverse, it reverses the sequence of characters in the buffer. So instead of hello, it becomes all H. Finally, when we print SB, it outputs the reversed string. This method is particularly useful when you need to manipulate strings dynamically, especially when revering text is part of your process. It highlights how string buffer provides built-in methods that make string manipulation more straightforward and efficient, which ties into our broader theme of working effectively with mutable string objects in Java. Let's take a closer look at the string buffer capacity method. In this example, we start by creating a new string buffer object called SB. When we print out SB capacity, it shows us the default capacity, which is 16. This is the initial size of the buffer that can hold characters before needing to expand. Next, we append the word hello to SB and again check the capacity. Since hello is short, the capacity remains unchanged at 16. This illustrates that adding small strings doesn't affect the buffer size immediately. Then we append a longer string. Java is my favorite language. Now the total length exceeds the current capacity. As a result, Java automatically increases the buffer size. The new capacity is calculated using the formula old capacity times 2 plus 2. So in this case, it becomes 16 times 2, which is 32 plus 2, making it 34. This automatic resizing is important to understand because it helps us manage memory efficiently when working with dynamic string data. It also ties into the overall theme of understanding how Java handles strings and buffers behind the scenes. Let's take a closer look at the ensure capacity method in the string buffer class. In this example, we start by creating a new string buffer instance and notice that its default capacity is 16. When we append hello, the capacity remains at 16 because the string is still small. As we append a longer string, Java is my favorite language. The total length exceeds the current capacity. At this point, Java automatically increases the capacity using the formula. Old capacity times 2 plus 2. So the capacity jumps from 16 to 34. Now, when we call ensure capacity 10, we're specifying a minimum capacity of 10, which is less than the current capacity of 34, so no change occurs. The capacity stays at 34. But then, when we call ensure capacity 50, we're requesting at least 50, which is more than the current capacity. Java responds by increasing it again, following the same formula. Current capacity times 2 plus 2, resulting in a new capacity of 70. This example highlights how ensure capacity can be used to optimize performance by pre-allocating buffer space, especially when you anticipate adding large amounts of data. It also demonstrates how Java manages internal buffer sizes dynamically, balancing efficiency with flexibility, which ties back into our overall discussion of string manipulation and memory management in Java. Let's take a closer look at the important constructors of the String Builder class. As you can see in this table, the String Builder class provides several constructors that allow us to initialize objects in different ways. The first one is the default constructor, which creates an empty string builder with an initial capacity of 16 characters. This is useful when we don't know the exact size of the string we want to build, but expect it to grow over time. Next, we have the constructor that takes an integer parameter, specifying the initial capacity. This is handy when we have an idea of the size of the string we're working with, helping to optimize performance by reducing the need for resizing. Then, there's a constructor that accepts a string argument, which initializes the string builder with the contents of that string. This is a quick way to start building upon an existing string. Finally, there's a constructor that combines a string and an integer, allowing us to set the initial string content along with a specific capacity. Understanding these constructors is key because they give us flexibility in how we create and optimize string builder objects, which ties back to our overall theme of efficient string manipulation in Java. Let's take a closer look at some of the important methods of the String Builder class. First up is the append method. This is used when you want to add a string or different data types like characters, booleans, integers, floats, or doubles to the end of your existing string. The append method is quite flexible because it is overloaded to handle various data types, making it easy to build or modify strings dynamically. Next, we have the insert method. This allows you to insert a string at a specific position within your existing string. So if you need to add some text somewhere in the middle, you can specify the exact index where the insertion should happen. Similar to append, insert is also overloaded, meaning you can insert different data types like characters, booleans, integers, floats, or doubles at that position. Then there's the replace method. This one is very useful when you want to replace a section of your string. You specify the start and end indices, and the method replaces that segment with a new string. It's perfect for updating parts of your string without rebuilding the entire thing. Following that, we have the delete method. As the name suggests, it deletes a portion of the string between the specified start and end indices. It's a handy way to remove unwanted parts efficiently. Another key method is reverse. This simply reverses the entire string, which can be useful in various scenarios, such as checking palindromes or manipulating data for specific algorithms. Finally, there's capacity. This method tells you the current capacity of the string builder object, which is the amount of space allocated for the string. Understanding capacity helps in optimizing performance, especially when dealing with large or dynamically growing strings. All these methods together give us powerful tools to efficiently manipulate strings in Java, fitting perfectly into the broader theme of working with mutable string data structures for better performance and flexibility. Now, let's take a look at some important methods of the string builder class that we haven't covered yet. First up is ensure capacity. This method is used to make sure that the capacity of the string builder is at least equal to the minimum specified. It's useful when you know you'll be appending a lot of data and want to optimize performance by avoiding multiple resizes. Next, we have charat. This method allows us to retrieve the character at a specific position within the string. It's handy when you need to examine or manipulate individual characters. Then there's length. This one simply returns the total number of characters in the current string. It's fundamental for understanding how much data you're working with. Moving on, we have substring with just a begin index. This returns a new string starting from that position to the end of the original string. It's useful for extracting parts of a string when you know where to start. And finally, substring with both begin index and end index. This method returns a substring from the start index up to, but not including, the end index. It allows for precise extraction of string portions. These methods are key tools in efficiently managing and manipulating strings with String Builder, helping us write more flexible and performance-optimized code. Let's take a closer look at the difference between String Buffer and String Builder. First, regarding synchronization, String Buffer is synchronized, which means it is thread-safe. In practical terms, this means that two threads cannot call its methods simultaneously without causing issues. This safety feature is important when multiple threads are accessing and modifying the same string buffer object. On the other hand, String Builder is not synchronized, so it is not thread-safe. This allows it to be more flexible and faster when used in single-threaded scenarios because it doesn't have the overhead of synchronization. Speaking of efficiency, because String Buffer is synchronized, it tends to be less efficient compared to String Builder. String Builder, being non-synchronized, performs better and is more suitable for situations where thread safety isn't a concern. Finally, a bit of history. String Buffer was introduced way back in Java 1, making it a long-standing part of Java's core library. String Builder, however, was introduced later, in Java 1.5, as a more efficient alternative for single-threaded contexts. So, understanding these differences helps us choose the right class based on whether we need thread safety or optimal performance in our applications. All right, let's take a look at this final slide, which compares the performance of String Buffer and String Builder in Java. What we're doing here is measuring the time it takes to append a string multiple times, specifically 10,000 times, to each of these classes. First, we start with String Buffer, which is synchronized, meaning it's thread-safe but can have some overhead due to synchronization. We record the start time using system, current time millis, then create a String Buffer object initialized with Java. Inside the loop, we append tPoint repeatedly. After the loop completes, we calculate and print out how much time it took. Next, we do the same with String Builder. We again record the start time, create a String Builder with the same initial string, and perform the same number of appends. The key difference here is that String Builder isn't synchronized, so it generally performs faster in single-threaded scenarios. By comparing the two times, we see that String Builder typically outperforms String Buffer because it doesn't have the overhead of synchronization. This highlights a crucial point for performance optimization. Choose String Builder when thread safety isn't a concern to improve efficiency. Connecting this to our overall theme, understanding these differences helps us write more efficient Java code, especially in performance-critical applications. So, always consider whether thread safety is necessary before deciding between String Buffer and String Builder.